There's a stack of new stuff and a stack of old stuff. So make sure that you grab what you don't have because it might not be for everybody. So these are old. There's this new stack, right? Where's the new stack? Let's go over it. So these are old, okay? So if you grab a few more each. Maybe I should help instead of being pretty chaotic. Anyone missing the glass packaging slides? Both or just one? Second one. Anyone else missing the glasses? There's a bunch left. There must be people that right here. So, other than that, you have a series about shocks. And by shocks, basically, that was a while back. And also one problem statement for the example. And there's one double-sided new sheet that we may have time to cover a little bit later today. So welcome back, everybody. So what I will do today, I'll review what we've done. Again, this is a long time. On shocks, we'll do a problem together based on this. And then we'll start with some new material. If you have not collected your second homework or exam, I have them with me. I'll return them after class if you would like. Also, I'm grading your third homework, and I should be done in returning it to you hopefully this week. And we'll go. So with this, any question?
I have a question about the homework, so we can answer that later.
Which one?
Why did they split up in the 20 and then the high 20 and the low 80?
That's just the procedure they decide to do. It's a bit arbitrary how they do that.
Okay.
Yeah.
How could that possibly help with anything though?
We'll talk about it later.
Okay. So I'm super curious.
That's
about
okay. That. So when I return the homework, I have a lot to discuss about anyway, so we'll do that. So, I don't know if you guys remember when before the Glass Institute, we talked about shocks, okay? We described what are shocks, okay? So, you're going to be dealing with a rapid change of acceleration over a short period of time, okay? We discussed that three factors basically define the shocks, but if they are linked together, so if you know two of them, the third one is actually known. So you have the maximum acceleration, the duration, and also the velocity change. In a way, it's not exactly true, but it's all linked together. One thing we're going to see more and more is that the velocity change, okay, corresponds to the area under the curve, okay, of the acceleration with time, okay. And that makes sense if you think about an acceleration being the integral. So if you integrate the acceleration with respect to time, you get the velocity change. And that is associated with the amount of energy associated with a shock. Okay? We discussed at the time there was different types of impacts that could be recorded or created. So for packaging application, what we use typically is those two. Okay? An F-sign type of impact, which is typically what we notice in real life. Okay? And a trapezoidal, because it's really hard to have a square form impact shape. So a trapezoidal impact is also going to be used quite a lot, particularly with the thing we're going to discuss a little bit later today with the damage boundary curve. So we introduce the concept of coefficient of restitution, which has to do with the ratio of the rebound velocity over the impact velocity, and that has to do with an object falling will hit the ground, unless it's some object might just stick there if it's really heavy and you have a lot of deformation, or if you're dealing with a bag of something, you may have an object that falls and have zero rebound velocity, but oftentimes it's going to have a certain rebound. So the total velocity change has to do with the ratio of impact to rebound. Okay, that is why, and this is something I said I should have corrected here. Okay, it can be equal to, basically, that would be the lower limit, but this could not be equal to, because object would not rebound back twice as the impact velocity. So the minimum velocity change occurs when your object is falling, okay, and has no rebound velocity. So the total velocity change, if you want, is the impact velocity minus 0. That's it, or plus 0. And here, you will have, if the object were to rebound as fast as the impact velocity, so that gives you the range of the total velocity change. Then, I don't know if you remember, but we went into an energy balance, okay, to try to find out some more of the physics of the impact. So what we derive and what we establish is we started with the potential energy associated with the drop height, initial drop height, which is h, okay? mgh gives us the potential energy. The kinetic energy is linked to the acceleration. As the package is falling down, it is accelerated due to gravitational acceleration, therefore its velocity increases. And we all know that the total change of potential energy plus the total change of kinetic energy should be equal to 0. And here we obviously neglect any type of friction with the air and drag and all these things, okay? So whatever is gained or lost in potential energy as the package falling off, it's gained due to acceleration, okay, in kinetic energy. So in here, what we showed is that at the point of impact, where we know the impact velocity is going to be square root of 2gh, if we replace everything in here, we find that this is actually conserved, where the kinetic energy at the moment of impact is equal to the initial potential energy that we have with that drop. So all of this was established. From this, what we've said and what we worked on is, okay, what we have now is an object falling, and to think about it, to protect against shocks or impact, what we'll use is a cushioning material. And we're going to discuss and work on what will be the area needed and thickness needed a little bit later. But we're going to have a cushioning material, and that cushioning material is there to absorb that impact. So we already know that how we represent physically those cushions is with a spring. Okay, so what we did here, okay, is that we looked at what is the energy of a spring with respect to deformation, and that energy is equal to 1/2 stiffness of the spring or the cushion times the deformation square. So going from this, what we know, and when we thought about it, okay, is like you're going to have your package falling off, okay, and you're going to have your product at the impact, okay. So you're going to have a lot of energy, and that energy is going to be transmitted to the cushion as it's going to be deforming. So how it's going to be absorbed is going to be absorbed all the way until you have the maximum deflection. Okay, so we introduce a new variable here, delta max, okay, which is the maximum deflection. So when the cushion has deflected in such a way that the object reaches 0 velocity again, from impact velocity to 0 velocity, that means that all the energy of the impact has been absorbed by the cushion. Okay, so what we did here is that we set the deformation as the maximum deformation. We know at this point, all of that energy must be equal to the energy of the impact, either with the kinetic equation or the potential energy equation. So once we've done that, we solved it, we obtained an equation here that links the maximum deflection of our cushion to the mass of our product, gravitational acceleration, drop height, and the stiffness of our cushion. So that's one thing. Other parameters that might be of interest for us are obviously the maximum acceleration. So to get there, what we did is we linked the force of a spring to a deformation of the spring. Okay, so we know that the force of a spring using Hooke's law was equal to minus k times the deformation. If we just worried or interested into the magnitude of that force, so we're gonna drop, if you want, the minus sign, because that minus sign indicates that the force is opposite of the deformation, right? So taking the absolute value of this here and replacing our expression for the maximum deflection, we obtain a different equation for the maximum force. That would be the force the cushion is exerting on your product at the point of maximum deflection. So we know that also that force, any force, can be represented by mass times acceleration. And if we replace it, we obtain an equation that gives us the maximum acceleration as a function of these variables. And then we spend quite a lot of time on this equation to try to make sense physically of what it indicated, and also try to make sure that it made sense. Okay? So what we looked at here, we noticed that the maximum acceleration was proportional to the square root of the height. So the higher the height, the higher the maximum acceleration. That makes sense. We also mentioned here, or observed, that if everything else is constant, if you increase the cushion stiffness, you're going to have a larger acceleration for a certain drop height. That makes sense as well. If the cushion is stiffer, it's not going to deflect as much, and you're going to have higher impact or acceleration. And then we spend time about the mass. Okay? So what this indicates is as the mass increases, you get a lower acceleration. Do you guys remember why we got this? Higher mass, lower acceleration. Yes?
Isn't it because it's the cushion doesn't have as much, like it won't have as much of an impact because the mass is so large? I don't know if I'm explaining that right.
Somewhere like this. Okay, so what's going to happen, okay, is the way to think about it is that if you have a very light object, even if you have like a super soft cushion, right, as your object falls on that cushion, or if it falls together, if the mass is very little, okay, it doesn't have enough inertia to deflect the cushion, right? Okay, so that means falling on a cushion or on a hard surface is not going to make much of a difference. As you increase the mass, if everything else is constant, the idea is that that mass will have more energy to deform that cushion, okay? And that's what the benefits comes in, okay? Because now, from the moment of impact to the maximum deflection, your object goes from impact velocity to zero velocity. You guys agree with me? So the longer time it takes for that to happen, the lower will be the acceleration. That means if your cushion is deforming more, okay, that means you go from impact velocity to zero velocity over a longer period of time. So therefore, you're going to get a lower maximum acceleration, okay? So that's what's happening here. The mass is not a mistake, okay, here. It is there because as the mass increases, if everything else is constant, okay, that means that deformation, you're going to have a larger deformation, and therefore the velocity change is going to happen over a longer period of time, and you're going to get a lower acceleration. So if I jump ahead here, okay, this is what we discussed. The heavier the product, the smaller is the maximum acceleration, assuming a well-designed cushion. And that little sentence here means that your cushion does not, assume that your cushion does not bottom out, okay? Because your cushion has typically what's called a working length, okay? So that's a distance by which it can be deflected and still work, okay? Past that point, it's basically bottoming out. It's just you crush so much of it that if you still have more energy when the cushion is deflected by its working length, it's basically going to be an impact with a hard surface, right? Because it basically compress all of it, and then you just touch whatever is after this, okay? It's going to be a hard impact. So if your deflection is so much that you pass the working length, then you're going to have a large acceleration because of this, and it's what's called bottoming out, okay? So this was what we just discussed. Going back just a little bit, and that's an equation we're going to be using as well, is we can play with a little bit of math, okay, here, a little bit of algebra, and transform that equation here into an equation that links the maximum deflection to the maximum acceleration. And what we've done here, you should be able to follow that, but we multiplied the numerator and denominator by the same factors, 2gh, okay? And what we did is we identify that this term here, m over k 2gh, is actually 1 over the maximum acceleration squared. By doing this, regrouping those two, you end up with 2gh squared at the top, okay? And you end up with that equation. So it's just, bless you, it's just a way to rewrite this equation to link different things together. And we're going to use that a little bit later. Any question on these things? It's very important that you understand the physics, okay, of that conservation of energy, potential energy to kinetic energy, and how we link that to the deformation of the spring, and also how that equation for acceleration here, physically, what we just described, it's important that you understand these things. So then we talked about a few shocks, a few facts about shocks. We mentioned that probability that the package will be dropped from a height greater than 1 meter is minimal, okay? Package received many drops from low heights and greater heights and so on. Unitized load. So you guys understand what is unitized load? It's basically loads that are on pallets. Okay. There's little control over the drop orientation with small packages. With larger package, usually half the drops are on the base. And we also discussed that. What you guys remember what we mentioned? Would it be worse for a package to get a drop on a corner or an edge, or would it be worse to have a drop on the base?
It's better on the corner, right? I think.
Why?
Because there's 2 cushions, hopefully.
Okay. What do you mean 2 cushions? Okay, on the 3.
Yeah.
Okay. Daria.
I'm gonna go in the corner, like pushes in that kind of acts as a cushion.
Yeah.
In and of itself.
So in a way, it's kind of a trick question, right? Because you can argue both ways. It depends what I mean. What is worse for the product? Okay. So if you're really talking about the product, the corner is good. Okay. And that's all assuming that that deformation is not so much that you hit the product. But when the corner deforms, okay, it actually acts as a cushion. Okay. And you're right, one, that if you have cushion on all of the faces, they're also going to be there. But as the corner deforms, it acts as a cushion. So typically you're going to have less acceleration, okay, on the corner or edge drop than if you have it on the flat surface, okay. But you messed up the box, okay. So that is a more of a aesthetic type of damage. But if that box is actually what the consumer sees, that can have a big influence on the purchase. So a heavier package has a lower probable drop height. Okay, so this we mention as well. And one of the reasons, okay, is if any types of package that are handled mechanically on conveyors, they're going to be exposed to the same kind of drop height, okay? Because if the conveyors are typically 30-inch, so waist high, so if they fall from this, it doesn't matter if it's 50 pounds or 5 pounds, right? Okay? So, and if a lot of things are carried waist high, so typically, okay, weight does not necessarily have a large influence. So that's why people are not too happy about this. And where is this reflected is in drop test sequences. We're going to talk about it a little bit later, but a lot of standards will basically dictate, if you want to test for drops, they're going to establish the drop height based on the weight of your product. some people don't like to do that. They rather drop everything from a certain height regardless of the weight. So that's something we're going to see a little bit later. Handles, we talked about this. If you have handles or handles on your box, typically it will lower the distance between the bottom of your box and the ground. Therefore, if it were to be dropped, okay, it's going to have a lower impact. And we talked about this as well. So these I'm not going to go back, but these establish or illustrate some of these statistics. And last time that I was teaching you, okay, we stopped there, the shock amplification for the critical element. In a way, this was discussed a little bit for your homework 3 in the SEC paper. And we're going to talk about these papers when I return your homework. I want you guys to have your homework when I discuss that. And I know that some part of that SEC paper was a little bit advanced, okay? But the objective and the main conclusion of that paper is pretty simple. So what this discusses here, okay, is very similar to what we've done with the magnification factor. Actually, the magnification factor sometimes is also referred to as an amplification factor, okay? But if you think about it, okay, an impact, whereas you have the acceleration as a function of time, look like a half sine wave. So that's how we describe it. So therefore, a little bit, so it looks something like this, right? And we discussed that it's basically half a sine wave. So there's no reason for an excitation, if you want, or an input to a system. Either it is a vibration or associated with a drop. If you have something like this, it's likely that the response of some component of your product, okay, is going to be linked to, if you want, the frequency, or if you want, the time or the duration of that impact, right? Because remember, the frequency is the time it takes for a full cycle. So it's linked to that period, okay, or the half period, if you want. So this links the acceleration or peak acceleration response that is felt by the component, okay, to the acceleration of the input, okay? So what we have here, it's a bit simpler than what we have because it's all tabulated. What we have is if you know the natural frequency of your critical component, which was given in a lot of problems before, and you find out or you're able to know the frequency associated with the input of the shock, okay, that has to do with the shape of that half sine input or square wave if you want, you're going to be able to calculate the amplification factor. Yes?
How do they find out which frequency breaks like an internal component? Like, is the thing plugged in when you run the test?
No, but typically not. So what you do...
Does that make sense what I'm asking?
Yeah. So you're trying to find... You're asking what frequency is going to be causing damage.
Yeah.
So it's not necessarily the frequency that's going to be causing damage. Okay, it depends on the input, right? If you have like very little amplitude, it's not going to change anything, even if you excite it at the same frequency, right? Because you're going to have dampening on things like this. What they identify as the critical frequency is not the critical frequency, but the natural frequency is basically it will put your product on a vibration table, they will run a sweep, and they will observe where your product gets into resonance, right? That's a natural frequency. Then, depending if those frequencies are really present in the distribution environment, then they can break, okay? And they can break due to vibration, but often they will break because of shocks, okay? So it depends, okay? But if you know the natural frequency, okay, you can go to that table, for example, and look at what is the ratio between the natural frequency and the input frequency, and find the amplification factor. So that will be, and let me just show you something before I talk a little bit more about it. So if you have an impact that is a solid line like this, okay, just remember that this is very similar to if you have a sine wave, okay? So what you're looking at, and typically you're going to know the duration of the impact, which is here identified by tau. Okay, tau is half the period. Okay, so if it's a 50 millisecond impact, that means that tau, just half the period, will be 50 milliseconds. So tau is half the period, and therefore is 1/2 times the inverse of the input frequency. Does it make sense? So the input frequency, therefore, is going to be 1/2 times the duration of the impact. So if it's a 50 millisecond shock that has been, you recorded it, you had an accelerometer or something like this on your product, and you measure this, you know that the input frequency is going to be 1/100 milliseconds, okay? And knowing this, you can go back to that table, and if you know the natural frequency, you calculate that ratio, and then you're going to have the amplification factor. Now, if you knew that this impact was, I don't know, 100 Gs, that means that your component, if it's, let's say, if you have a ratio of 4 and your amplification factor is 1.27, that means that your critical component is going to feel 127 Gs, okay, for 400 G impact. Does it make sense? Mm-hmm. So we're not going to do many things here, but if you were to use that equation, I don't think doing a problem, an example on this, any helps in any ways. It's just relatively straightforward. If you calculate the impact, the input frequency, you go into that table, you find the amplification factor, you just multiply, and that's it. So the next step I want to do, let me pause that for a second. I'm going to go on the board and I'm going to work on the problem statement I send out to you. It's called Example Shocks. So you should all have one copy of this. If not, there should be more around. Does everybody has this statement? Yes? Let's see. So, what it says here is that you have a 40 kilograms product shaped as a 30 centimeter cube that can sustain a maximum shock of 50 Gs. So this we're going to discuss a little bit later. Do you need a statement? Is there a few extra? Anyone else? So that means that the product fragility is known, and that has to do with what we're going to talk a little bit later, the damage boundary curves. So it is assumed that the product's sensitivity to shock is independent of its orientation, so I can't simplify things here. So that means we run a bunch of tests, okay, putting it on this bottom surface, side surface, and they basically find out that it's going to break with the same type of impact. There's no big variation depending on its orientation. So, sci-fi approach, so a sci-fi investigation established that the product should be protected against 1.5 meter drop. And what is asked here is calculate the modulus of elasticity of the material needed for cushioning if the working length of the cushion is equal to 50% of its initial thickness, and if the cushion covers the entire surface of the product. Okay, so let's write down what we know, okay, and go from there. You'll see it's not too bad. So we know first, let's see, the mass of your product, 40 kilograms. Okay, we also know that by side is 30 centimeters, okay, so your product is assumed to be, like this, 0.3 meters. So that means, okay, as it's mentioned a little bit later, you're going to have a cushion underneath this thing here, okay, and the cushion covers the entire area. So the area at the base, we can call that A0, is going to be equals to this, okay? So 0.09 meters squared. So that's the importance of that dimension. We also know that the maximum acceleration that the product can sustain is 50 Gs. Okay, so maximum acceleration. So that means it's 50 times the gravitational acceleration, which is 9.81 meter per second squared. Okay, calculate this. This is 490.5. No, yes, meter per second squared. And in a lot of the papers you're going to see in the packaging industry, they just use G's a lot. Okay. For academic purposes, I would like to convert that to meter per second squared. I think it makes things easier. Orientation is not a big deal. And then from the sci-fi, we assume that we should be protected for drops from 1.5 meters. And what it's asked is to calculate the modulus of elasticity of the material needed for cushioning if the working length of the cushion is equal to 50% of its initial thickness. Okay, so that means, okay, I discussed a little bit what the working length meant, okay, this morning. So if we design to really just achieve that protection, you don't want to overpackage. What all of that statement means, it means that the maximum deflection that we can accept with our design, okay, it has to be equal to the working length of the cushion. Does it make sense? So it's going to compress all the way to its maximum. Okay? Does it make sense? So if you understand this, that means that the maximum deflection is going to be 0.5 times L0. Okay? And this is initial thickness of the cushion. So your cushion, if I were to draw this, this would be A0, this would be L0, okay? So we don't know L0 yet, okay? So that's what we're going to be trying to find, okay, at some point. What else do we know? We know what is asked us to find is the modulus of elasticity, okay? And if you remember, when we established an equation for the modulus of elasticity, we linked a few things. Let me write this down just in case if you remember. We talked about stress was equal to the modulus of elasticity times the strain, okay? And we had the force over the area equals the modulus of elasticity of deformation over the initial length, like this. So we reorganize this as follows. Okay? And we mentioned that this was K in a way. So we found from this that K was modulus of elasticity A0 over L0. So in here, we know that the modulus of elasticity is linked to the stiffness of the cushion, okay? So that will be K times L0 over A0. So it's totally normal, you did not remember that, okay? It's, if you needed that, this was on the equation sheet for the first exam. So, where do you go from there? So we have two unknown in a way. So that stiffness here is unknown, okay, and L0 is unknown. So I'm going to just go back to the slides a little bit to show you what we can do, okay, and try to so the equation we derived that involves deformation and maximum acceleration were here. Okay, so you had this equation here for the maximum deflection. But it's not very useful in this form, right? Because we have the mass, we have the height, but we don't have K, so we cannot find this guy directly. What we do have is the maximum acceleration, okay? And the maximum acceleration from here, okay, will be useful, okay? Because it's going to allow us to find k. To be even quicker, okay, if you remember, is that we have this equation that links directly the maximum deflection to the acceleration with 2gh over a max. So we're going to make use of that equation first to be able to find the maximum deflection, and consequently, we're going to be able to find the initial thickness of our cushion right away. So if I go back here and blank this out. So here, what we have is we know that delta max, maximum deflection, is going to be equal to 2gh over a max. So if you replace the numbers here, it's going to be 2 times 9.81 times 1.5 divided by 490.5. Calculate this, that will give us a maximum deflection of 6 centimeters, 0.06 meters. So that implies that the thickness of our cushion, which we're going to need in here, is delta max over 0.5, that's times 2, 12 centimeters cushion. So in a way that's pretty thick, but think about this. This is a 40 kilogram product. So 40 kilogram, okay, it's 88 pounds. Okay, so that's a heavy type of product. So a thickness like this will make sense for a product such as this. From the equation we had as well, okay, we have to find K. So we had that the maximum deflection is equal to the square root of 2mgh over k. So if we raise both sides to the square and we solve for k, you find that k is going to be equal to 2mgh over delta max squared. Replacing these numbers here, that'll be 2 times 40 kilograms times 9.81 times 1.5 divided by 0.06 squared. If you calculate this, you'll find a K value of 327 times 10 to the 3 newtons per meter. So that's the stiffness of our cushion, okay? And that means the modulus of elasticity is going to be K L0 over A0. And if you replace everything here, 327 10 to the 3. 0.12, 0.09. Calculate all of this, you find a modulus of elasticity of 436 times 10 to the 3 newtons meter squared. So that's pretty much it. So in here in this problem, the difficult part is really to identify and write down everything we know initially. And I would say this is something that is probably not the most intuitive, okay? So every time you're given a working length, okay, let's say of 50%, that means that your cushion can deflect by this amount before it bottoms out, okay? So the tricky part for us through the analysis was to understand that means if we design in such a way that we don't want to overpackage, we need the maximum deflection to be equal to that working length. Okay, that's what this means here. Okay, so if you want, you can write that delta max here. We wanted it to be equal to the working length. Our cushion. So after that, what we had to do is look at the equation and what we can find from which equation. We could have done different routes to find the answer, but that should be relatively straightforward. So that was a quick example for a calculation based on what we applied. If you want to double check as well, one thing you can always look is that you can calculate the maximum force, right? Using mass times acceleration, or mass equals k times the maximum deflection. And you will see that in both cases, they should get the same answers. So before I let you go, okay, I have something to ask you, okay, and you're going to have to think a little bit. So everything we have done so far is obviously for vertical impacts, okay, because it's object falling up due to gravitational acceleration and then impacting the ground. So in distribution and transport, you often have a series of tests for horizontal impacts, okay? And can anyone tell me when you're going to get horizontal impacts? What would be example? Yes?
Something's in a truck and it breaks and the stuff moves forward.
That's good. Anything else?
Anything tips over, like pallets if you want to.
Okay, yeah. In conveyors as well, if you have chutes and things like this, when they have lateral impact. There's a really classic example is with rail cars. If you have rail transportation, when they couple the rail car, you have a big horizontal impact as well. So everything we've done here, could we use that physics that we developed for vertical impact to apply to a horizontal impact?
You use trig, maybe?
Trig. So yeah, that would not work. But it's a sneaky way to do that. It has to do with the basic of everything. Okay? All the physics, when we started with the energy balance, we started with the potential energy, right? Okay? And what did we do? We assumed that the package was falling, okay? And at the moment of impact, it reached.
Wouldn't you do like a free body diagram and you just tilt it? So, no?
Wouldn't you
Yeah.
just be saying that the gravity is the acceleration of the product
Change
initially?
the
Isn't there no potential energy because there's no drop height?
I'm sorry?
There's no potential energy because it's at the same height.
Okay, that's right. So, what were you
You
saying?
change the axis of orientation, so
Okay.
the acceleration, instead of being gravity, it's whatever the acceleration, direction of motion,
Okay.
and then the distance between where it starts and where it hits
Okay.
would be the height.
Okay, but we didn't use gravitational acceleration much in that direction. We use it a little bit, but the basic of everything was the impact velocity, right? So what we can do is typically on a horizontal impact, you'll know, in a way you guys are right, you know the impact velocity, or you'll be able to find it, okay? If it's a rail car coupling or you have a package basically on a conveyor hitting a wall. So what we can do is that if you know the impact velocity, you know it's equal to 2gh, okay? What you can do is you can find an equivalent drop height. Does that make sense? That will give you the same exact impact. So vi squared is equal to 2gh, okay? So the equivalent drop height, okay, is just vi squared over 2g. If you use this, okay, meaning you know you have a horizontal impact and you can measure, sometimes measure acceleration, you can do that, or one thing that you often will know is at what velocity the package hits the surface or the coupling that happened and everything. So if you're able to, if you know that impact velocity, you can find an equivalent drop height and use everything with basically worked out on the horizontal impact with that h. Does it make sense? Okay? And assume that it is equivalent that, let's say, like an impact at 6 meters per second is the same thing as a drop height from 30 centimeters. I just made that number. I have no idea if it makes sense or not, but that's the equivalent, the way that you can use these for horizontal impact. And there's not a lot of people here, okay? Remember this, okay? So this is your, this may come back on an exam, so you need to know, explain how you can link horizontal impact to vertical impact. So welcome back, and hopefully it's the last stretch of the semester. I'm working on establishing projects for you guys. So we have a few more series of slides. I'm going to also establish the exam date very soon, and I'll let you know, and we'll go from there. So welcome back, and I'll see you Wednesday. Or if you did not pick up your second homework or exam, you can come and see me. I'll give it back to you. Okay.
Thank you.